All right, welcome back. I mentioned this in class and I didn't get a chance to talk too much about it, so I wanted to make a video explaining why the complex numbers are not an ordered field. So just to review, an ordered field is a number system where we satisfy all of the axioms except maybe the completeness axiom. So we satisfy all of the adding and multiplying and distributive axioms and those order axioms. And our main examples are going to be things like Q and R. Those are ordered fields, and we've been using them our whole lives, right? Every time we make a statement like 3 is less than 5 or negative 10 is less than negative 6, we're comparing elements, we're putting an order on these numbers. And so in our class, we saw some facts about ordered fields, and one of the facts in the book was that if we take any element in an ordered field and we square it, then we always get a positive number, or 0. We get a non-negative number. And I'm going to prove this in a few minutes. But I want to show why this causes a problem for the complex numbers. So this causes a problem for complex numbers. And you might want to pause the video and see if you can see why. So the reason is that this kind of means that if the complex numbers were an ordered field, then since the square of any element has to be non-negative, that would mean that I squared has to be greater than or equal to 0. And of course, what is I squared? Well, it's negative 1. Okay, so that means that negative 1 has to be greater than or equal to 0, which of course means that 1 is going to be negative. Going to be less than or equal to 0. And of course we can do the same trick with 1, right? 1 squared has to be greater than or equal to 0 by that same property, and of course this is the usual statement that 1 is greater than 0, and so we have a direct contradiction, right? So this is a contradiction here. And so what that shows is that these order axioms can't possibly hold for the complex numbers, because it would imply that 1 is both positive and negative. I guess we should have mentioned that 1 is not 0, kind of the overlap between those two statements. So let me prove now that we have this statement. So if A is an element in an ordered field, then if we square it, we're going to get something that's greater than or equal to 0. And so I'm just going to do two cases. So case 1, if A is positive, so if A is, well, let's do case 1. If A is equal to 0, then of course A squared is 0, which equals 0, so our case is satisfied. Case 2 is going to be if A is positive. Well, then I guess that's going to mean that I can multiply both sides by A. Right, so A times A is going to be greater than 0 times A. I just multiplied by a positive number. Right, remember, I can multiply an inequality. Let me rewrite it here. I can multiply an inequality by a positive number, and it stays preserved. And now we get A squared is greater than 0, which that's good. That's what we wanted to show. And now for case 3, let's assume that A is negative. Okay? So if A is negative, then negative A is going to be positive. So let me write this in words. So negative A is going to be a positive number, which means that now I can multiply both sides by that positive number. Right? I can multiply both sides by that positive number, negative A, and it's going to preserve my inequality. I want to pause and think about this, right? Negative A is a positive number if A is negative, so we're good. And then again, we're going to get negative A times negative A. It was one of the earlier properties, I think maybe one of the ones you did for homework, that this is going to be equal to a positive A squared. So in all three cases, we see that A squared is going to be greater than or equal to 0, so we are done. So thanks for watching. I hope maybe this gives some new appreciation for the order axioms and the real number axioms in general. Have a great day. Bye.